Okay, welcome back. Before I forget and I erase this, there's a meeting Wednesday, and then I guess there's a Smash Brothers tournament on Friday. Ooh, right in here. I think what they're trying to do is have one on the big screen and the other on this side over here, which I think we can set up because we do have two HDMI cables, so great. So all of y'all show up to this. Wow, 7 to 10.
You know it's going to take the whole time.
Well, if it wasn't so late, I'd show up. But, oh well.
You can bring the family and they can all hang out.
The 1-year-old goes to bed at 6:30, and this starts at 7.
So close.
You want a screaming child, and then there's a 3-year-old who goes to bed at 7, so he'll start screaming at around 8.
They're babies.
He knows.
It's too early.
Now the 9-year-old, she'll stay up and then fall asleep on the floor, and the 7-year-old, he'll play the entire time, nonstop.
He'd probably be a dog.
Yeah, he's actually pretty good for a 7-year-old. All right, binary trees. So today, let me start talking about the actual material. Where'd the marker go? It's gone. So binary trees is going to be your next actual data structure, not an abstract one, that we are going to study. And it's our first tree structure. It'll be the simplest one, hopefully, simply because it has the word binary. All right. So let me think best way to explain this. So there are, first off, before we begin, make sure you keep in mind that there are multiple binary trees. And the one, we're going to talk about binary trees in general, and then we're going to talk about the first instance of a binary tree, which is the binary search tree. Okay, so give me some numbers.
5.
14. 2.
Negative 30.
19. Negative 3.
Okay, how many is that? 7?
Yeah.
Let's do one more. Oh wait, no, 7's perfect. I lied. Okay. So binary tree, we're going to start with this one, create a node, and then it's going to have 2 offspring, hence the word binary. We'll put the 14 over here, and then the 2 over here. And then, so we get the 14 there, the 2 there, we'll put the negative 30 here, the 7 here, the 19 there, and the negative 30. Hey look, every node has 2 children, which are also its own node. Alright, so that's a binary tree. So this is a good picture of what a binary tree looks like. The root is right here, and then the branches, you see what they did there? Has 2 branches, 2 other nodes, which are subtrees. Because if you think about it, this right here is a binary tree, as well as this over here, and then of course these ends are binary trees. And if you're on a node that has no children, you're called a leaf. Got it? All right. So first off, with this binary tree, if we wanted to find the value 19, how long would that take?
2 searches.
Well, you have to search the whole tree, right?
Yeah.
So I want to make sure it's clear that this is a binary tree, but for our purposes, it's not very useful at this moment. So we're going to do something completely different. Well, not completely different, something very different. We add the 5. The rule we're going to do is if the number is larger, it's going to go to the right. If the number is smaller, it's going to go to the left. All right? So, therefore, you're going to add 14. Where does it go?
Over.
To the right. Now we're going to add 2. Where does it go?
11.
To the left. We're going to add negative 30. Where does it go?
Left twice.
Yep, left twice. We're going to add 7.
Right, left.
Right, left. Did you study this already?
No.
Okay, good. That means my explanation is
What are you
right.
doing here?
Where's 19 go?
Right, right.
And then the negative 3.
Left.
Left,
right.
left, Now it can't go here
Yeah, left,
because
left.
-3 is not greater than 2. So it goes left, left, right.
I couldn't see the 2. But I see it now. That's better.
Much better?
Yes.
Excellent. Okay. This is also a binary tree, but this is called a binary search tree because it's made for searching. All right. Now, if we want to find 19, how do we get there?
You have to compare each time to see if something's bigger or less than.
Yeah, so we're at the 5 and we compare. Which way do we go?
Right.
We go right. Do we just cut off something?
The left side of it.
The whole left side. Ah, that's great. So hopefully you can see that if this tree was huge, we just cut off a huge portion of the tree. So we're at 19, where do we go? I mean 14, sorry.
Right.
Right again, cut off, well, this could be huge again, but it's not. And then we're at 19. Ooh, what's the big O?
Thinking log it in, it's splitting it in half per
So-
iteration.
Overall, correct. But let me,
Or would it be in log of n because there's also comparisons?
no, in log would be if you had to do it multiple in times, but we're only going down log times on average, although it's not completely the case. Because watch, what happens if I put in, do we have room? Oh, we have room. So the first one would be 5, and then it goes to the right, to the right. Look at that, to the right. Am I going off the board? I am.
So it'd be in times then.
Yes. So,
It's in the worst case then?
yes, there we go, perfect. So, in other words, here's a worst case scenario where it's definitely in. Average case is probably closer to log of n. And then best case is if the tree was completely filled out perfectly, and then it would still be log of n. Okay. I do need to stop for a moment and let's go make a little chart. Because I haven't done this in a while. We have an array, right? Yes. And we have a linked list. And now we have what's called a binary search tree, which is what I put up here. How far am I off the board? Excellent. All right. So, let's think about this. If we want to, let's go. We'll do, ooh, this is where things get a little tricky. Push back. What was that on the array?
Worst case in.
Right, worst case was O of n. Oops, let me write that this way. Worst case is O of n, but average and best are both O of 1. Excellent. How about linked list?
O of 1.
O of 1. Does it make much sense to do this on a binary search tree? No.
Not really.
So I'm going to put a question mark. All right. How about just, we'll just call it add. We're just adding a variable somewhere. That's the reason why I wanted to make sure that these two, you're clear that this is not an operation you really do on a binary search tree before we start. So add, we're just adding a variable to the list.
So they're the same.
It's the same for, actually, we'll just do O of 1. And then it's O of 1 here. If we want to add a variable to the binary search tree, what's the big O of that?
Log of n
For,
for the best case.
yeah, the best, oops. Let me stick with my scheme was worst average and best. Best and average are both gonna be, you said log of n?
Mm.
Log of n. And then worst is,
Yeah.
yeah, O of n. Okay. So it kinda looks like it's losing here. Search, ooh. Searching on an array. Depends if it's sorted or unsorted, right? So let's go with unsorted right now.
Oh, okay.
Yeah, so it's O of n. How about a linked list?
Okay.
Yep. And a binary search tree?
Log of n in the best case.
Yeah, so worst, average, and best. Average and best is O of log of n. And worst is O of n. Okay, we're winning there. All right, we're gonna see a pattern, by the way. How about, let's call it remove. There's an element in here you want to remove. Or remove something from an array.
Okay.
O of n.
Okay.
O of n.
Log of n in the best. Okay.
Have you seen the pattern yet? O of n. So O of n, the worst case, because if it's basically a linked list, then it's a linked list. But if it maintains some type of what's called balancing, so if the tree isn't too skewed, then it's log of n. All right. And what was the other one? Oh, I'm going to do this. You know the subscript operator on an array? Right. Just to make sure this is clear. What's a subscript operator on an array? What's the big O?
Oh, one.
It's always O of 1 because it just jumps straight to it. Now we could do it for a linked list, but that makes a linked list. Yeah, it's O of n. Binary search tree. You don't know how deep these are, right? So you actually have to traverse the whole thing. Although it kind of doesn't make sense. Because where are we jumping to, right? It doesn't, I mean, you could say O of n, or you could just say it doesn't make sense. I'm trying to get, we're gonna start looking into certain operations just don't make sense on certain data structures. That's just how it is. Okay. So, which one's the best?
Depends.
Depends. What does it depend on?
What kind of data and how much you have?
Maybe not the amount, but
What you're doing with it?
what we're doing with it, right? So when would you want to use a binary search tree?
Searching for things?
Search. When you're doing a lot of what? Well, they're searching, right? So it does win on searching. Although we didn't do the sorted array. Maybe we should do a sorted array. Let's do that. So sorted array, push back doesn't make any sense. Because you don't push to the back, it's sorted. How about adding? How long does it take to add something to a sorted array?
Oh, okay.
O of n. Well, you could do a binary search to find the position. You then have to shift all the elements over, so that makes it O of n. All right. How about to search?
Log of n.
Now it's log of n, and that's guaranteed because of our binary search. And remove.
Log of n.
It's log of n to find it,
Oh,
but then you gotta shift everything down, so then it's back to O of n. Subscript, well that actually makes sense in this case. Okay. How about now? Because searching the sorted array wins. So if you're just searching, sorted array is gonna win that one.
You still are faster on removing and adding.
but removing and adding, you're slower. So in other words, if you're doing these three operations a lot, of these data structures, the binary search tree is the winner. If you're pushing to the back, or and I didn't put pop, but pushing and popping, probably linked list, and then let's see, if you're just doing searching, actually the array is going to be better. But if you want the subscript operator because you want to jump down to different points as quickly as possible, then the array is going to win. All right, how are we doing? This table should be, you should be able to generate this table, or at least think about it. Because these functions are going to change depending on what data structure we're looking at. All right. Great. That was a quick, what was it, 10, 15-minute explanation of binary search trees. Any questions before I go over the slides to figure out what I forgot about? Nope. Great. All right, binary trees, so it has a root node and each tree is a subtree. It is very important to realize that this is a tree and this is also a binary tree. Y'all see that? So if you think about this, the binary tree is really composed of a node of other binary trees. So what type of data structure does that make it? Iterative or recursive? I guess is the better way to put it. Well, it's recursive. So when something defines itself by having itself inside of it, that's recursive. All right, so here's some more pictures. Root node, right child. So you have A, it's the parent, right child of A, left child of A, and a directed branch. It is important, I didn't draw it up there, but these arrows go in one direction. We will talk later about data structures where they go the other direction, but for now it always goes down because it's a tree. If an arrow goes up, that's going to be bad. All right, binary tree with one node, and then those are the next three are the only possible binary trees with actually with two nodes on the next one. And then D is one of the instances with three, because you can also have these as three. So think about it, with one node there's one, with two there's two, with three there's four, or did they do five? 1, 2, 3, 4, 5. There's actually 5 instances with 3 nodes. We're just trying, the number is not too important right now, but just trying to give you an idea of what different binary trees can look like. Every node has at most 2 children. Note that they can have 0 or 1. They can't have negative children. That doesn't make any sense. And hopefully it comes as no surprise that those arrows I was drawing up there are simply pointers to other nodes. So you have your root. We'll go up here. Root, which is a pointer to the first node, which is 5, and then 2 other pointers. All right, and they love terminology, so let's go throw a bunch of terms at you and see how many you remember. A leaf is a node that has no children, because if it's at the end of the tree, it's a leaf. U is a parent of V if there's a branch from U to V, aka 5 is the parent of 14 because there's a branch going from 5 directly to 14. Very important, it is a single branch. 5 is not the parent of 19 because there's not one branch, there are multiple branches. So I guess you could call it the grandparent in this situation. But we're just talking about parent. A parent is one branch. Length of a path, or there's a unique path from the root to every node. If you look at the binary tree, hopefully you can tell that that's the case. mainly because you start and then you go down and there's no way to loop back. The length of the path is the number of branches. Okay? Level of a node is the number of branches on the path from the root to the node. The root node is 0. So let's go take a couple of looks. So 5 is on level 0, 2 is on level
1,
-3.
3.
Okay, good. Just trying to trip you up. All right.
It's early.
It's height of a binary tree is the number of nodes on the longest path. So the height number of nodes on the longest path. So the height of this tree is 4. All right. We're doing great. Okay. Any questions on these terms? Your lab is to calculate the height of a tree, as well as other things. See, binary trees are a dynamic data structure. This is opposed to an array, which is generally considered static, because an array you have static and then you just manipulate the data, unless you have to create a new one. But the binary tree, you can add to it, remove from it on the fly as it's working, so it can grow and shrink. Similarly to a linked list, where a linked list is dynamic because you can add and remove from it as well. How do you make a copy? I don't quite see why this is a good time to talk about that, so we won't. Binary traversal, on the other hand, is a great thing to start talking about, but before we do that, we probably should code something up. Y'all like code? I thought so.